Welcome, everybody, to this next presentation in the series of Community of Practice webinars. The Risk Informed Performance Based Principles and Policy Committee, RP3C, of the ANS has been putting on these events for the past 5 years. Presentations and recordings of the events are available to the public at the ANS website under the tab RP3C. There are now almost 50 such recordings available. The purpose of these webinars is to offer practitioners of concepts and methods related to risk-informed and performance-based approaches, RIPB we call it, a chance to share their knowledge and experience. I would expect that such practice is used for implementing nuclear technology and also to evaluate its safety. The purpose of RP3C is to help modernize ANS standards. The Nuclear Energy Innovation and Modernization Act of 2019 associated modernization with application of RIPB approaches. Congress reiterated and reinforced this idea in 2024 with the Advance Act. There is growing realization within the nuclear community that conventional, prescriptive, and deterministic approaches are not going to support increasing use of nuclear technology to play its rightful role for the benefit of society. Socializing alternative approaches could drive changes in industry and regulatory practices. ANS offers the CoP files on its website to serve as a knowledge repository of the experience from a wide range of practitioners in the field. We hope that more people will use this knowledge base to speed up needed changes in the state of the art as well as the state of practice. These events are generally scheduled for the last Friday of each month, although we have made an exception, and this is the first Friday of April, and you'll have the pleasure of, I think, two community of practice events in April. I will turn the presentation over to the presenter today, Fred Grant, and he will introduce himself and the topic he will address. Thank you. Fred?
Thank you, Prasad. As Prasad said, I'm Fred Grant. I'm a principal at Simpson Gumpertz Heger, SGH. I have about 20 years experience specializing in external hazards risk for nuclear power plant structures. Currently the chair of the ANS ASME Joint Committee for Nuclear Risk Management Seismic Working Group. That's a mouthful. It's the technical working group responsible for the seismic requirements and the PRA standards. I'm going to share with you all a presentation today on research that was sponsored by EPRI and led by SGH in risk-informed performance-based design methods for external hazards. This research culminated in a report that was published in September of 2024. And if we have time, depending on how things go and if there's engagement and questions, I may also give a preview of some follow-on research that's currently ongoing related to more specifically risk-informed performance-based codes and standards selection and justification for structural design. This research, the scope started with an initial assessment of the kinds of challenges that practitioners might face when implementing the so-called licensing modernization project approach for structural design and for external hazards design. And the objective was to identify needs for future research or additional guidance to facilitate implementation and practice. So again, the The objective of this research was evaluating ongoing industry activities, so it included some literature review related to risk-informed performance-based design for external hazards specifically. NEI 1804 is a guidance document that NEI published for implementation of the licensing modernization project. However, both the licensing modernization project and NEI 1804 were really focused primarily on internal events. The developers had internal events in mind, and external hazards have some nuances that really do introduce some complications when trying to implement the guidance from 1804. So that was the objective of this project, was to flesh out, how would you take that guidance from 1804 and apply it to external hazards, and identify any challenges, gaps in the guidance, best practices, and to publish those results and identify areas for future research. The project included a literature review, some stakeholder input through surveys and workshops with advanced reactor developers and other practitioners. And we really wanted to make it concrete, down to earth. So we've included a demonstration example that applied the framework, the guidance from 1804, to a stylized problem. Some prior work had done some example work before. There's an RIL report, I think it's 2021-04 or 05, I think, from Southwest Research Institute that implemented a risk-informed performance-based design approach for structures for external hazards, for seismic in particular. And the example there focused really on a component, so like a shear wall, and looked at how risk-informed, RIPB methods could optimize like the sizing and so forth of an individual component. This research expanded the scope of a demonstration example and included a stylized example of a whole advanced reactor plant. So several systems, many different components, had a very sort of a simplified PRA. We'll get into that some more. The two green bullets below this presentation will focus on those two green bullets. We'll walk through the demonstration example, and then I have a quick slide on a few insights, some gaps, challenges, and best practices that were identified. And then I have the report number down there in the last bullet for anyone who's interested. That report's available for EPRI members and EPRI Advanced Nuclear Technology section sponsors, ANT sponsors. So to start with the demonstration example. So this figure shows the various steps that the demonstration example walked through. Again, we wanted to make this very concrete, try to implement each step in the whole process for RIPB design using a PRA for external hazards, and see where we might run into challenges and where the guidance was unclear on exactly how to proceed, and then identify those and develop recommendations to flesh the guidance out. So we start with the plant response model, which is item number 1 here. It defines the seismic event tree. We developed an example seismic event tree and some fault trees for a simple example that we thought was representative of multiple advanced reactor designs. The second part of this is to define dose functions. So for each licensing basis event or event sequence in this event tree, there's an end state, so a plant damage state, and each of those plant damage states should correspond to some dose function quantified as a dose at the exclusion area boundary, the plant boundary. And those need to be represented in terms of like a best estimate dose and a variability. So, 5% confidence and 95% confidence level of radioactive dose at the exclusionary boundary. The next element is number 3 here, the seismic hazard analysis. So we need both a mean and uncertainty around that, so 5%, 95%. We came up with just some kind of representative. I think it was for the central and eastern U.S. Seismic hazards, so we had something to run some quantifications on. Number 4, seismic fragility evaluation. So this is kind of where some novel work was done. At the early stages of design for a new advanced reactor, we don't really have much design information. So normally when you do seismic fragility analysis, all the seismic PRA methods and the guidance are developed for analyzing an operating plant. That's kind of the background of seismic PRA. And so there's a ton of guidance if you have an actual structure or a component available to tell you how to develop a seismic fragility for an operating plant. When you have just a design and oftentimes a very, I don't know, sketchy kind of a design, right? It's an early in the design stage, you don't have much detail, specificity in the design. That makes it a little more challenging to develop that seismic fragility. So this report demonstrates how to develop those seismic fragilities in the early design stages based primarily on the design criteria, the structural design criteria that are selected. So that was a useful development, I think, from this research. Then step number 5 is risk quantification. So we use this PRA model, the seismic hazard and the seismic fragility information, roll it all together into a risk quantification step. So for each event sequence here, we quantify the probability of each end state, each LBE essentially, the annual probability that LBE will occur, and its corresponding variability, uncertainty, 5%, 95% confidence. And we have the dose functions from step number 2, and those get plotted on a so-called FC chart or frequency consequence chart from NEI 1804. More on that later. This risk quantification is used to categorize each LBE. So these FC chart results is used to categorize each LBE as either a anticipated operational occurrence or AOO, a design basis event, DBE, or beyond design basis event, BDBE, depending on how frequent the events are. This is all following the NEI 1804 guidance. Then the next step is we take those results and we evaluate the acceptance criteria from LMP and NEI 1804. There's some regulatory requirements, some cumulative risk metrics, quantitative health objectives, and so on. So we take the results of this risk quantification, the frequency, consequence, outcomes, corresponding uncertainty, and we can evaluate the adequacy of the plant according to some acceptance criteria and the guidance and some regulatory requirements. And then we use, if the plant is acceptable, then we can use that, if the design meets the regulatory requirements, then we can use that information also to categorize both the LBEs, the licensing basis events, and structure systems and components. So we developed the preliminary safety classifications depending on the outcomes of this risk quantification. At that point, we have a choice here, depending on whether we find these risk outcomes acceptable. We have an option to iterate on the design, right? We can do all kinds of things. This is kind of where the creativity comes in the design stage. We can strengthen the design. We can add additional barriers. We can apply what's called just generically called special treatments to just augment, modify the design criteria or the design, and then input that information back into the analysis, rerun the quantification, and follow the process again. So this risk-informed performance-based design approach in LMP and 1804 is kind of fundamentally an iterative process. It's intended to follow a graded approach where you start out with simplified models and simplified characterizations of different elements, and you can refine as the design becomes more mature and to optimize the design. And then ultimately, once everything is resolved and the design is stable, then we document the outcomes, the seismic design criteria, any special treatments that were imposed, the licensing basis event, and SSE safety classes, and so on. So that's an overview of the process. The next slides will step through the example that we did in this research project. So the NEI 1804 guidance defines several processes that go into execution of this RIPB design. It starts by defining the licensing basis events. So this involves identifying all the kinds of failures that could occur for the various SSEs and systems in the plant. And then there's a process for classifying the LBEs and the SSEs. So that was illustrated in the previous slide, where the LBEs are modeled and quantified and then classified by plotting them on this FC chart. So if the LBE frequency and consequence falls in this upper region right here, where the frequency is higher than 1e minus 2 per year, then it's characterized as an anticipated operational occurrence. It's classified as an AOO. If it's in this region here between 1e minus 4 and 1e minus 2 failures per year, then it's a design basis event. If it's below 1e minus 4, then it's a beyond design basis event. And each of these, 1804 provides some guidance for treating each of these kinds of LBEs differently. So there's a process for classifying them, and then requirements for handling each type. It also, 1804 has a process where you iterate between the design and the PRA. So I mentioned that in the previous slide. That's demonstrated in the example problem. The example problem also demonstrates defining performance-based seismic design criteria. So the example that's exercised in the EPRI research project focuses on seismic. Conceptually, it could be extended to other hazards. It's probably some additional research would be warranted to flesh out exactly how to do that. But we focused on seismic for a variety of reasons, namely because the seismic risk methods are probably the most developed among the external hazards. It also includes a code and standard provision selection process, so some exercising of how do you select codes and standards, using both the example exercise in the EPRI research uses both commercial codes and standards for non-safety related components and nuclear codes and standards for safety related components. I mentioned that this report introduces an approach for estimating the initial seismic fragilities based on just the seismic design criteria before there's detailed design information available. Demonstrates checking of the regulatory acceptance criteria following NEA 1804, and the example demonstrates, investigation of some options for design revisions based after a first iteration of this kind of analysis. So this is the event tree that was developed for this example. It's generic, supposed to be representative of many different kinds of advanced reactors. We have 5 top events. We have a seismic initiating event. The 5 top events are the reactor building failure, the reactor vessel and support integrity failure, failure to insert SCRAM, and system for heat removal failure, and then backup heat suppression failure. So 5 different systems. and uh, uh, let's see, 6 different LBEs, 6 different LBEs, size 1 to size 6. 4 of the LBEs result in radiological release. Uh, 2 do not. And this red line here shows one event sequence or LBE. The event sequences in the 1804 framework are called LBEs or licensing basis events. We broke down one of the 5 systems into a little more detail than the others. So each of these, the reactor building is modeled with like one basic event for simplicity, one fragility. The similar for RVNS and SCRAM. The system for heat removal, we broke down a little bit more. We had 1, 2, 3, 4, 5 different components representing, a coolant system, a reservoir, a pump, control cabinet, a couple of valves. And we modeled that system with a fault tree, modeling how different failures of individual components. We just put a little more detail into one of the systems so that we could play around with how changes in design criteria might be affected by the complexity of the modeling. So for each item in this model, we made some initial assumptions. We classified each system either as safety related, non-safety related with special treatment, or non-safety related. For the safety related components, we assigned design criteria following traditional light water reactor, nuclear codes and standards, performance requirements, safety factors, and so on. For non-safety related with special treatment, we used commercial codes and standards with some special treatment, some additional, augmented requirements necessary to achieve a desired performance target. And then for the non-safety related components, we use commercial codes and standards, commercial factors of safety, commercial performance requirements, and so on. So this use of commercial codes and standards, particularly for the non-safety related with special treatment, NSRST components, is we think critical for realizing the kind of cost-saving potential that RIPB design has to offer. Switching from the safety-related paradigm, the nuclear paradigm, to the commercial paradigm for design requirements. That's really where I think the nuclear industry stands to save a lot from using a risk-informed performance-based method. So that's what we try to exercise here. There's one of the open questions is, well, can you achieve the kind of required performance to ensure adequate public health and safety using commercial codes and standards? So that's what part of what this research was exploring and demonstrating, really. So once we assign these initial design requirements, each of these choices determines the seismic fragility and the resulting performance. So you can determine what your structural reliability is, what your seismic reliability is, once you know what your design requirements are. There's obviously some variation once you get more specific in your design. You might have a component that has some design criteria for seismic, but the design's actually governed by some other kind of loading, maybe a high energy line break, or maybe a wind load or something like that. So there may be additional margin, for example, beyond the minimum that's specified in the design criteria. But as a first cut to start to think about RIPB design for your plant, you can use just the design criteria to develop your reliability metrics. So we take the design criteria and we take our event tree model, and what we can do is quantify based on the fragilities that were developed and the seismic hazard that was selected. We can quantify the mean risk. We have a corresponding dose consequence, as I mentioned in an earlier slide. We have uncertainty on each of those, and 95% and 5% confidence uncertainty both on the event frequency and on the dose. And then those, what are called frequency consequence outcomes, are plotted on this so-called frequency consequence chart, FC chart. This one, size 3, this LBE, plots onto this location in the beyond design basis event region, and that has certain ramifications for how to treat beyond design basis events in NEA 1804. The two LBEs that don't result in any radiological release, I guess you don't really have to plot those, but those show up here with the frequencies shown with essentially 0 dose consequence. And then the remaining LBEs plot as shown here, size 4, 5, and 6, each of which has a corresponding dose consequence and a frequency. So what we see here from this initial cut, so we specified safety-related, traditional LWR nuclear design criteria for the safety-related components, commercial codes and standards for non-safety related with special treatment. And we find that some of the initial designs result in frequency consequence outcomes that exceed the FC target. So this blue line is the so-called FC target. In NEA 1804 and LMP, it's not strictly an acceptance criterion. It's really more of a design goal. It could be acceptable to have LBEs exceeding that frequency consequence target, but it gives a guideline that tells you, if all your LBEs do fall within that FC target, then you probably have a design that will meet all the regulatory requirements in terms of reliability and dose. So it's not a strict requirement, but it's desirable to meet it. This initial design had some outcomes that went beyond the FC target. That's not a favorable result, especially early in the design. And so, the next step is, what do we do about that? We also had one LBE whose 95% confidence dose fell beyond the 25 rem dose limit. This is in NEA 1804. This is more of a strict requirement. And its 95% confidence frequency falls within the DBE range. So NEI 1804 says this should be treated as a design basis event. That means it should be addressed with a design basis accident. And the regulation says we can't have any design basis accidents whose high confidence dose consequences exceed this 25 rem at the exclusionary boundary. So that result here, this purple result, requires us to implement some kind of design revision in order to meet the requirements of 1804 and the regulation. There's another check that we do. There's a number of other checks that we do related to cumulative risk and other regulatory criteria. For this example, we just looked at one of those. It's the cumulative risk requirement. There's some others like quantitative health objectives and so on that we didn't get into, but for the cumulative risk requirement, there's a different threshold. It's 100 millirem at the exclusionary boundary. And the requirement is that the sum of frequencies for all LBEs exceeding that 100 millirem at the exclusionary boundary has to be less than 1 per year, a frequency of less than 1 per year. So just to walk through that a little bit, we get rid of the no consequence LBEs. Those are not relevant. So we're just focusing on the LBEs that have exclusionary boundary doses exceeding 100 millirems. We don't have to worry about the uncertainties for this check. We're just looking at the mean frequencies. We look at the frequencies for each of these LBEs. So this one's about 1e minus 4, 1.3e minus 5, and so on. We add those all up together and we get about 1.2 E minus 4. Then we have to check to confirm that the total frequency for LBEs exceeding 100 millirems is less than 1 per year. In this case, for our 4 LBEs that we're considering, we're well under that threshold, like 0.1%, less than 0.01% of the threshold. And so this is, if these were the only failures that we had to consider for this design, that would demonstrate that we've met that requirement. We're way under the requirement. So a little bit of insight here is that probably external hazards are not going to challenge this cumulative requirement. So the contributions to this 1 per year is probably going to be governed by lower dose events that are higher frequency up here, maybe in the AOO region and the DBE region. And the 1804 and LMP process sort of precludes LBEs resulting in significant doses from occurring in the AOO and the DBE region by defining a design basis hazard level, which is for seismic, it's equivalent to like a safe shutdown earthquake, an SSE. So the process says specify design basis hazard level or SSE, design all your safety related stuff to survive that, design all your non-safety related stuff to ensure that it doesn't interfere with your safety related functions at that SSE or DBHL level. And what that does is it pushes all of your failures resulting from external hazard initiating events really down into the BDBE range. It should. And so all these LBEs, these beyond design basis LBEs are going to be very small compared to the 1 per year limit. And so external hazard is probably not going to contribute much to that event. Again, this is seismic only. There will be any other hazards, internal event, external events, and so we would expect this sum to get bigger once we have a more involved, more detailed, realistic model. There are other cumulative risk metrics, like the quantitative health objectives. Those weren't evaluated in this example for simplicity because that would require like radiological dispersion analysis. Once you have dose release, how does that move and what's the population look like around the plant? That's just too complicated for this and really not unique to external hazards. I'm sure there's some unique aspects, but we were trying to focus on external hazards. So the next step, once you have those initial design frequency consequence outcomes, is to consider potential design revisions. So those design revisions could take on all kinds of different forms. Some examples, you could reconsider the seismic design criteria. You could impose special treatments on SSE designs. So maybe you would require some, maximum demand to capacity ratio, DCR, for some structural components. Like maybe you require that the DCR stay below 0.8 or 0.5 or something like that to increase the reliability and pull these frequencies down. You could reclassify SSEs depending on where these fall. Maybe you take an NSRST component and you make it safety related. That would change the corresponding design criteria. You could change your plant design by figuring out ways to limit the dose consequences, provide additional protection barriers. We can refine the performance targets, either the capability performance targets, or those correspond to limit states for structural design. So maybe we say rather than characterizing failure for a structure as like the onset of concrete cracking, maybe we could allow some, non-trivial drift because that doesn't really compromise the function that's credited in the PRA for that structure. So we can refine sort of the behavior, the limit state that characterizes failure of individual components. Or we can do some combination of the above.
Hey,
So this is where
so
the creativity comes in. Yep.
that's actually, I think this goes to a question that we've got in the chat, and I mean you could come back to this later on, but the question here is that you've described the process in your presentation as risk informed and performance based. The reference is to slide 4, but I think that you just kind of hit on this. So would you be able to talk a little bit about the performance based attributes of the process and identify them as separate and distinct from the probabilistic risk attributes?
Yeah, so I think a lot of what we're doing indeed is the risk informed part, right? You do the PRA and you get some risk insights, and then at this point, this is where we use the risk insights to potentially change the design criteria, right? So we can impose some additional margin or something to change the design criteria. And then what we can do is we can specify, for example, that a building's or a component's performance is required to achieve some certain performance targets. And the performance targets can be for like structural design, external hazard design, is normally characterized as like a reliability target and a capability target. So for a reliability target, you might say, for example, that this structure has to have a failure frequency less than 1e minus 5 per year due to seismic events. That's the performance target, for example, baked in for safety-related components in ASCE 43 for LWR nuclear structures. So that design standard is actually performance-based, right? It specifies here's your performance target in terms of reliability. And it also has, although the limit states are not used for LWR design traditionally, it has a set of capability targets or limit states. You can go to limit state A, B, C, or D. Each one corresponds to a different level of like structural damage or drift as a result of seismic loading. And so those are capability targets, right? So and as you select a different limit state, that affects what kind of like acceptable structural performance looks like. And so that's the performance-based element, right? If we can define what the structure has to do, what its function is, what kind of capability or limit state would inhibit that structural function, and if we can define how frequently it should be allowed or can be allowed to exceed that limit state or fail that function, then we have performance targets. We have reliability targets in terms of how frequently it can be allowed, and we have capability targets in terms of what kind of behavior is permissible that won't fail its function. And then, so once we have those performance targets, reliability and capability, then we can define design criteria that will ensure that those performance targets are met, that those reliability and capability targets are met. So that's the performance base, right? We're basing the structural design criteria on some performance target that's informed by a risk analysis, including the whole, system and interactions. And then we're specifying certain design criteria like a SSE or material strengths or things like that, that all come together to ensure that reliability and that capability is met, right? So that capability is met with the target reliability. So I hope that answers the question. All right, so after we revise the design, I have a nice little animation here that shows how the quantification results change. And what we have is, the one event that was in the DBE range is no longer a DBE. And the other events, the 95% confidence, reliabilities, and capabilities have now fallen below the FC target. So this is a much more risk balanced, much more desirable design. The special treatments that were selected we limited the DCR, basically a pretty simple special treatment, just adding margin into these components. And in this case, this was sort of postulated as being the best cost benefit of several options considered, but certainly there are other design options that could be implemented. So kind of the key takeaway here is that this framework does indeed allow optimizing the design for cost benefit as the design progresses. So some insights. That was the design example. What do we learn from that and from the literature review and the stakeholder engagement? One challenge from this process has been identified by many folks. It's the initial PRA at early design stages can be challenging to develop because there's limited site-specific data, limited plant-specific data, limited design information. And so those initial PRA insights can change significantly as the design progresses. Another interesting challenge, and we've seen this in practice, not just in this research project, but certainly in stakeholder engagement in the research project, is that this is really an interdisciplinary process where folks who normally wouldn't work so closely together really do need to work very closely together. So there's a whole bunch of lingo here, like LBEs and reliability and capability targets and things like that structural designers normally wouldn't be familiar with, but they're going to be incredibly important for how they do their work and how this design takes place. And the iterative process of doing an analysis is normal for a PRA. Not so normal for traditional structural design workflows. The PRA folks, they know frequencies and consequence and stuff like that, but limit states and other terminology and concepts are not as familiar. So this is what we've seen is this is a much more integrated and collaborative workflow than your traditional plant design process. And I think that requires some things like cross-training and maybe just different organizational solutions to address that unique characteristic. Benefits, we talked about this a little bit. Certainly there's opportunity to make our plants more cost effective while maintaining high levels of safety. And code and standard selection is kind of a interesting part of the whole NEA 1804 and LMP process. 1804 sort of lays out how to go through this process and plot LBEs on your FC chart and get frequency and consequence outcomes. And then it says select codes and standards based on this. So there's not a lot of detailed guidance on how to do that, at least for external hazards and structural design. But there is a lot of potential there for risk optimizing or cost optimizing your designs by selecting appropriate codes and standards. And I think we'll get into that here in the next few slides.
Yeah, so just one question there, Fred, on the special treatments part of it. Another question in the chat here is, I think it's questions about the kind of the implementation of the special treatment. So like back on slide 10, you said the special treatment was to limit the demand to capacity. So in terms of how that actually looks, is that selecting different parts of a code and standard, like different requirements, or I think there's also a question about tracking and documenting special treatments. So maybe in terms of how this limiting the ratio actually works in practicality
Right.
in design space might give a little bit more insight there.
Yeah, I think every developer is gonna, every designer could be doing this differently. This kind of gets to my point about how this is a more integrated process, and it's a kind of a novel workflow. Those special treatments might be changing every time you do a sort of a design iteration. So it is, I think, important to track. I think ultimately, for at least for structural design, SSEs will have design criteria, right? Requirements. Some developers I've seen are using like requirements management databases. You could have design criteria documents, system configuration documents, and so forth. And those special treatments, I think, would be, they would live as design requirements in that kind of like design documentation. But yeah, certainly tracking and documenting, like document control, can be challenging, especially when the design process is moving fast and iterating rapidly and so on. So, good question. Yeah. Um, yeah, follow-up research. So, this research project, if you pull up the report, I think there's like several pages of areas that were identified that would benefit from some additional research and some additional guidance. There were two things that came out of it that were prioritized by EPRI and the EPRI members. One of them is, how do we use this method to select the codes and standards for structural design? I mentioned that LMP has limited guidance there, especially for external hazards and structural design. So there's some ongoing research there. The other thing is the other research area that was prioritized was treatment of very rare seismic events in RIPB design. So if you look at uh, the FC chart, what developers have found is that it's kind of difficult to keep to ensure that we're keeping LBEs out of like this range that are pretty rare beyond design basis and high consequence because like eventually at some point you will have a wind event, an external hazard event, a seismic event that fails your structures. Like no structures are completely impervious. And if structures fail, then it can be, unclear exactly how to characterize the dose consequences of the structural failures. So if you have potentially a large source term, and you have some structures that enclose it, those structures could fail and result in high doses. And it's really challenging to design them to achieve like a 5E minus 7 reliability. Like LWRs are not designed. I mentioned the design performance target for ASCE 43 for LWRs is like 1E minus 5 per year. So that's up here. And for really high consequence events, this FC chart would lead us to try to design our structures to 5E minus 7, which is down here. So this is kind of a trouble area, and there's some ongoing EPRI research to look into why that is and what we can do about it, especially because that's a very uncertain range. We're talking about potentially earthquakes that have never been seen before, 2G, 3G plus PGA. There's a lot of uncertainty in what that means exactly. How does it affect the plant and the structure? So, two areas of follow-up research. I have some more slides. Looks like we have about 10 minutes. I could get into, these are kind of bonus slides that I put together if we had time on some ongoing research on code and standard for RIPB design, but I don't know, Brandon, what do you think? Should we take questions or proceed ahead? I saw some activity in the chat.
Yeah, so I think the one thing that might, I don't know if it looks like maybe in like slide 17, to your point on the codes and standards selection, kind of what this, like how the special treatments are actually, selecting the different requirements. I don't know if there's a way to just kind of jump to that and kind of point out that like selecting kind of the difference between using how within a given standard or within, selecting between standards, how that does look at the special treatments. But if that's too much, then there are a couple other questions.
Yeah, maybe I'll walk through this one slide 17 that gets to that. I think that's what you were suggesting. So, and this, follow-on research for code and standard selection. This is just kind of an illustrative example here. So, don't take any numbers on this slide to the bank. I have a disclaimer on that at the end of the slide here. But the idea here is we have a nuclear standard ASCE 4319. We have the commercial standard ASCE 7. Again, focusing in here on seismic. 43 is a seismic. 7 covers wind and other loading as well, but has some seismic provisions. So focusing in on seismic, each of these codes has sort of design levers you can pull, right? It has ASCE 7 has risk categories 1, 2, 3, and 4. ASCE 43, like I said, has limit states and seismic design categories. Limit states A through D and seismic design categories 1, 2, 3, 4, 5. And each of those sets of criteria will specify a seismic fragility, essentially. So if you said, I'm going to design this structure to ASCE 7 risk category 4, that specifies a certain reliability. So if you open up ASCE 7, you could find the sort of specified reliability for each of these risk categories. Some of it's not super transparent. It's not like, here's your fragility. But it says, like a 1% failure probability in 50 years, something like that for collapse. And so you can interpret from that, you can derive structural reliability. So there's some uncertainty, you have a sort of a design point, and from there you can characterize like a seismic fragility. And then if you have a seismic hazard, right? So we have a seismic hazard, and you have some kind of structural limit state. So like for structural collapse in this case, you could put those together and get LBE frequencies, basically, or event frequencies, frequencies of exceeding that structural limit state. So in this case, these gold bars are the different seismic design categories from ASCE 43, the nuclear code. I mentioned before that the target reliability for SDC 5 is 1E minus 5. And then the reliability goes down, basically the frequency goes up as you go into lower seismic design categories. And then, if we convolve each of these fragilities with the site-specific hazard, we can get event frequencies. So it's the annual frequency of exceeding this structural collapse limit state for ASCE 7 risk category 2 and 3, risk category 1 and 2, risk category 3, and risk category 4. And so we have structural reliabilities for each of these as well. Now, translating that into the LMP 1804 framework, here's our FC target. We can plot these reliabilities for the nuclear code, the 4 different SDCs, as frequencies of structural collapse, frequencies of exceeding that limit state. And then we can plot each of these ASCE 7 structural design criteria, the reliability is achieved with each of these ASCE 7 structural design criteria. You can see those in the dotted blue, orange, and gray lines here. Sorry, it gets kind of messy. And then imagine we could quantify let's say like the high confidence dose corresponding to collapse of this structure, right? So, and we could say that the dose of the exclusionary boundary, if we collapse the structure, is limited to 20 rems. Then we can infer from that a target reliability of about 1E minus 4. So we just go into the FC chart, assuming this is our design objective. Again, it's not a regulatory limit, this FC chart, but it could be a design objective. And we can specify that we want to achieve a reliability performance for this event, which results in a 20 rem dose of about 1E minus 4. And we can plot that here again, and we can see that SDC4, SDC5 from the nuclear code, and risk category 3 and risk category 4 from the commercial code, they all achieve that desired performance. So um, it, any one of those codes would theoretically achieve the required performance for this component, for this structure.
Thank you, Fred. Yeah, no, I think this is really great. I think, putting the quantification on it really illustrates kind of the different options there. I think we probably got time for one more question. There may be some offline follow-up about somewhere on the performance base, because we've got about 3 minutes left here, and I want to get everybody out on time. So the last question is,
Brandon,
yeah,
I just want to mention for everybody's benefit, Fred did not mention ANS 2.26 specifically, but people should note that all those ASCE categories are really based on the ANS standard 2.26. And, so the combination of existing standards come together as a way to use all the information that Fred has provided, so you can go directly to the standards and get what people are asking about special treatments and other things, because 2.26 actually addresses the performance-based aspect also in Appendix C of the standard. So that should answer the questions about special treatment or that some people have asked. So just thought.
That's a good thanks Prasad. That's a good point. I'm glad you brought it up. It is in the back of my mind. There are some, I guess, limitations to 2.26. I think sort of the classification scheme in 2.26 is based on unmitigated release. So that can introduce some complications. For LWRs, 2.26 wasn't really used. Everyone just used limit state D. But if you are going to try to specify different limit states in ASCE 43, so limit state A, B, C, or D, or the SDCs, 2.26 definitely has some very useful, helpful guidance on how to do that. It's interesting, and based on interactions with the NRC to date, it seems like the NRC structural folks are really not very familiar with 2.26. 2.26 was used sort of traditionally, mostly in DOE space, not commercial light water reactors. And so I think there's a little bit of a learning curve in the industry on what does 2.26 entail exactly, and how can it be used. I think there's some members of 226 online
Yeah,
today.
I'm a member of the working group for
Yeah.
2.36, Fred.
Okay, good. And I think I understand it that the committee or the working group is looking at revising it too, which might make it even more useful for this kind of risk-informed performance-based design.
Well, the revision is going on, and also there has been a request from a developer, to use it for a nuclear plant design. So,
Yep,
these things are in process. But in the
excellent.
meantime, there are ways of addressing the unmitigated consequence within the standard itself. As
Good.
I say, Appendix C of the standard, provides a lot of guidance. So anyway, thank you. Brandon, I think you can wrap up now.
I was just gonna, just real quick, Fred. There was a question about the kind of specific scope of the ongoing rare seismic events. Do you have maybe just a sentence or two more on the primary focus of the very rare seismic event, RIPB design?
Yeah, we did some sensitivity studies. We did some investigation that sort of the hypothesis going into that project was that, and the prevailing wisdom, I think, was that as you go up into the very high hazard ranges, the uncertainty in the hazard gets so large that it's effectively meaningless, and you can't develop meaningful risk insights because the hazard ranges are so big in the high hazard regions. Sorry, the uncertainty ranges are so big in the high hazard regions. We did some investigation into that, and it's interesting because while the hazard uncertainty gets really big in the high hazard regions, the fragility uncertainty actually goes to zero, basically, right? Like you get up to a certain level and everything is failing, right? All components are, failure probability at 1.0. And so the actual uncertainty and the risk or the risk insights up in those high hazard regions is relatively small. So there's sort of a sweet spot in between where you haven't failed everything yet, but you're up in the high hazard regions where the hazard has a lot of uncertainty. And we're looking at various ways on how to deal with that. So one way is to recognize like the 5e minus 7 threshold, the kind of the screening threshold for LBEs in the FC chart. It it's supposed to correspond to like quantitative health objectives, but it doesn't take into account like the conditional probability of early fatalities or something like that, given some large release. So there may be some other factors in there that are not really accounted for in the development of that FC chart. There may be some other sort of qualitative arguments that could be made. So, for example, if you have a 5G earthquake, 5G PGA earthquake at a nuclear plant, chances are everything in the vicinity of that nuclear plant that you're trying to protect, all the public health and safety in the vicinity of the nuclear plant, is going to have already undergone some significant problems, some damage. And so the marginal risk contributed by having the nuclear plant there can actually be small and down in the margins. So I don't know. There's a few different directions that could be taken. I think the outcome is probably going to be sort of a multifaceted, multi-pronged, semi-quantitative, qualitative set of arguments or recommendations for how and why these low frequency external hazard events should be treated differently in risk-informed performance-based design.
Well, thank you so much, Fred. Appreciate your time today. I apologize for everyone for running over a little bit, but this was a very interesting and lively discussion. I think the only note to follow up on or to shoot Kathy an email if you're looking for that continuing education credit. But other than that, appreciate everyone's attention and interaction today. And that'll be the end of this community of practice, and hope everyone has a good weekend.
All right. Thanks, everyone.
Thank you all.
Thank you.